far we have studied compactification of type 2 string theories on Calabi-Yau folds. And as we saw, this gives n equal to 2 supersymmetric theories in 4 dimensions. So we'll come back to type 2 and see how to reduce the number of supersymmetries. But today we'll consider heterotic string theory compactified on Calabi-Yau. Okay, and see what kind of low energy physics we get from that compactification. So heterotic. So the task will be to first determine the spectrum and then the interactions involving those fields, and the kind of spectrum we expect at low energy will be the bosonic spectrum, massless bosonic fields, there will be metric, which is part of the gravity multiplet, so it will have a gravitational partner. Then you have a set of complex scalars which are denoted by phi I. So these are scalars of the chiral multiplet. Its complex conjugate will be the scalars in the anti-chiral multiplet. Okay, so I will not write down separately the anti-chiral multiplet scalars, and then there will be a set of gauge fields. So these will have their partners, super partners, which will be Weyl fermions. The gauge fields will have their super partners, the gauge zeros, which will be Majorana fermions, and that's it. Right? These are the massless fields that we expect in the low energy theory. And so you have to find out. Okay, metric is of course unique, but what kind of scalar fields we get, what kind of gauge fields we get, and then write down an action involving the scalar fields and the gauge fields.
Originally we also had 2 forms.
Yeah, but 2 forms in 4 dimensions can always be dualist to scalars, right? So they will be all included in the scalars. Okay, so before we determine the spectrum, which of course will be the first task, it will be useful to write down the most general 2 derivative action that you could have. Okay, just like we did for type 2 for the n equal to 2 string theories, right? We saw that given the prepotential, okay, and the hypermultiplet metric, we can write down the most general action, okay, at least at the 2 derivative level. So one can ask, can we write down something similar for n equal to 1 supergravity? Okay, and here we will see that unlike in the case of type 2, there will also be potentials, okay, involving the scalars, because we know, for example, in global n equal to 1 supersymmetry, we can add a superpotential, okay, which generates a potential. The form of the potential that we will get will be slightly different in supergravity, but nevertheless there will be potential. So low energy theory action. So it turns out the low energy action is controlled by several functions. First of all, there is scalar potential, which will be a function of phi and phi bar. Then there will be superpotential, W phi. Okay, this is the data that we need in the chiral multiplet sector. But once you have gauge fields, we need 2 more functions, okay, which I will introduce in a few minutes. Okay, what other ingredient you need when you try to incorporate gauge fields. So with this, let's first write down the action involving the metric and the chiral multiplet scalars. So that action takes reasonably simple form. minus Gij bar phi bar del mu Ij bar minus Bf phi bar. Okay, there will be some more terms added here, so let me give some space. Okay, and let me now describe what these objects are. So Gij bar is del I del J bar of K. Okay, this is the metric in the field space that you calculate out of the scalar potential. This is a scalar potential.
Maybe phi bar. Meaning phi minimum phi bar.
Phi bar, yes, thank you. So up to this point, we had also in n equal to 1 to supergravity, right? If you remember, the vector multiplet action had this kind of structure. This is the superpotential. This is the potential. Okay. Vf has the following structure. Vf of phi bar is given by e to the k Gij bar diw djw bar minus 3 mod w square, where diw is diw plus w times del I is del phi I. Okay, so you recognize some terms. Okay, in normal any global n equal to 1 supersymmetry, you don't have the e to the k term. Okay. And the reason, okay, that this is still consistent with global supersymmetries, because whenever you see terms that you didn't have, they are actually accompanied by a factor of G Newton, which I have said equal to 1 here, right? Otherwise you should have a G Newton down here. We have said G Newton equal to 1, but actually if you want to put the factors of G Newton, there is a factor of G Newton here. Okay. Similarly, there is a factor of G Newton multiplying this term, right? That's why you don't see this term in standard case. And there is also a G Newton hidden here, right? That's why this minus 3 mod w square you never see. Okay. But otherwise this term is familiar, right? It's del w del phi I mod square. Okay. That's what you have in standard n equal to 1 supergravity, n equal to 1 global supersymmetry. Okay. So you can see also from this, okay, which will play an important role, that unlike in global supersymmetry, this potential is not positive definite. Okay, because there is a minus 3 mod w square sitting here. Okay. And this will allow us to construct ADS, supersymmetric ADS vacuum in these theories, okay, under certain circumstances. But this is something that is useful to keep in mind, that the potential is not positive definite in n equal to 1 supergravity, unlike in n equal to 1 global supersymmetric theories. Okay, so this is the full action if there are no gauge fields. If there are gauge fields, okay, we need more ingredient. Okay, just W and K, of course, doesn't tell everything about the action. So, if there are gauge fields, we also need a term that controls a gauge kinetic term, a function that controls a gauge kinetic term, which are denoted by FAB of phi. FAB of phi. This is an homomorphic function, depends on phi only. This controls gauge kinetic term.
can one think of this negative term serving as somewhat like a negative cosmological constant roughly?
Well, yeah, it's like a negative cosmological. It's not really cosmological constant because if W is 0, then this term is not there, and it's a function of fields, right? Cosmological constant. This is a negative term in the potential. Right? It's not a constant in any sense, right? So it's a negative term in the potential, right? If you want to call it cosmological constant, it's fine. Right? If W is, if phi is sitting at some specific value, right? And then if this whole thing is negative, then indeed it will serve as a negative cosmological constant. Okay, so FAB of phi is an analytic function of phi. Okay, the indices are the gauge indices. Okay, these indices here, which could be U1, which could be not a villain. This controls gauge analytic term. And then one more information that we need is how does the gauge transformation act on the fields, right? Normally we describe the action of the gauge transformation on the fields by giving the charges that the fields carry. Okay, that's when the fields transform linearly under gauge transformation. Okay. But here we will not make that assumption that the fields transform linearly, because although often it may happen, we will think of the fields parameterizing some manifold, okay, whose scalar potential is k. Okay. And now the action of gauge transformation will correspond to some killing vectors on that manifold. Right? Why killing vector? Because the Lagrangian is gauge invariant, right? The metric better be gauge invariant. The metric Gi is, in order that this is gauge invariant, this better be gauge invariant, right? These of course will be replaced by d mu, gauge covariant derivative. Okay? So we need a set of killing vectors for every generator. We have to specify what is the killing vector on the manifold that gives the action of that generator. Is this point clear? So that killing vector is what we will denote by xia. Xia is the killing vector on phi space that gives action of P. The P is the gauge generator associated with index anyway.
Sir, what prevents FAB from being some function of the metric?
Function of the
Metric G.
Well, FAB is not a function of the metric. You have to, because you have to be able to write down the kinetic term in a n equal to 1 supersymmetric way, right? That prevents FAB to be a function of the metric explicitly, and that have a hard derivative terms, right? Where it may involve functions of Riemann tensor and Riemann square and so on. But those will be hard derivative terms in the action. You are only writing the true derivative terms in the action. Right? At the true derivative level, right, FAB is not a function of the metric, just like this is not a function of the metric. Okay? This is just a function of the scalar fields only. Okay? So then the action is written, the gauge field action is written as minus 1/4 FAB 5 F plus A mu F plus B mu. These are again the cell dual parts plus Hermitian conjugate. And then there is another term in the potential which is minus dD. Right? These will be all covariant derivatives. Okay? So these d mu's will be replaced by appropriate covariant derivative, which will use the killing vector fields. So I have to just write down Vd and then you are done. Okay, the d term potential. So Vd phi bar is given by the following. It's half real of f inverse AP real AP dA is I derived K plus derived W over W xi. Okay, so this is the general structure that you have of the superpotential. Again, in n equal to 1 supergravity, this term is absent. Okay, K is just phi bar phi. Okay, so this will be just phi I. Okay, so this is I phi I, and this xia will basically carry the charge, because the more the charge the field carries, the larger is the killing vector, right? It moves more. Okay, so it will reduce. I mean, you can easily check that in n equal to 1, global n equal to 1 theory, this will reduce to a standard dA half dA kinetic d-term potential. Okay, but this is a general structure that you have for n equal to 1 supergravity. Is this okay?
This D is acting on K, it's acting on.
No, dA is just a number. This is number. This is not a derivative. This is a d-term. Yeah, this is a d-term potential. Yeah, this is dA dV, right? The square of t. Okay, contracted by this index. So these are just numbers, not operators.
So F plus is the same as we defined before.
Yes, F plus is the same as we defined before, the self-dual part of the field strength. Okay, basically F mu nu plus I epsilon mu nu rho sigma F rho sigma. If you are familiar with global supersymmetry, then this is probably familiar where it's coming from, right? Because you write down the gauge field action as integral d2 theta of W alpha W alpha. Okay, so W alpha is the field strength supermultiplet, chiral supermultiplet, and you can multiply it by any analytic function of phi without breaking supersymmetry, right? Because you have to integrate a chiral multiplet over d2 theta. Right? So normally in global supersymmetry theory, because you don't want to include hard derivative terms, you just integrate W alpha W alpha. Okay, that's the field. Okay, and that's what this FAB of phi captures. And this, as I said, is the generalization of the d-term potential. In global supersymmetric theory, when G Newton is set equal to 0, some of these terms go away and you recover the standard form. Okay. So I wrote it down, although not every part of this I will be using in the lectures. Yes.
Could you repeat the origin of that minus W mod square term? Minus 3W mod square term?
Well, origin meaning this comes from n equal to 1 supersymmetry. Right?
There
I mean,
the first term only.
no, but there is no k there, no?
No.
So there is no Gij there, it's just a flat metric. So what is the supergravity gives rise to this whole set of terms. Okay. The reason that you don't see this in n equal to global n equal to 1 supersymmetry, because this is multiplied by G Newton, okay, which is Heterotic. So in the limit G Newton goes to 0, this term will go away. That will recover the answer that we get in global supersymmetry. But the full n equal to 1 supergravity, right, once you couple to gravity, this term has to be there. Okay, so let's start now.
So in the phi space,
Yes.
could we put more structure, like could we put gauge fields which would act like gauging of the phi manifold?
Gauge fields. They will be
putting
like
the-
scalars. From the point of view of the space-time fields, they will be like scalars. Right? You are thinking of you have some object which has index around the phi space.
Yeah, so phi itself is a manifold.
Yeah, so
And
suppose you have an index on the phi space,
it
that
has
will just be a scalar, right? From the space-time viewpoint, that is another scalar. Right? So you add it to this system. So the point is, as long as you are dealing with scalars and vectors, right? This is a general structure, okay, of two derivative terms that you can write down. Right? What you are asking is maybe this Gij of phi, this phi space has more interpretation, right? Maybe it's a fiber bundle or something like that, which can happen, right? But that you are not using that in that structure here. Right? All we are using here, that this is a Kähler manifold equipped to the Kähler potential, and all these structures that we have seen here. Right? If there is a gauge invariant, there better be an isometry in the phi space, which describes the gauge transformation actions. Is this okay? Okay, so now let's get back to heterotic on Calabi or threefold and see what kind of fields we have. Okay, and then you have to start constructing the various terms which appear in this action.
Another thing, could you please repeat why in normal supersymmetry, I understood the G Newton
Yes.
goes to 0 part, but when we write down supergravity, don't we write down G Newton and then write down all the supersymmetry transformation?
Yes.
We do not really take the limit.
No, you write G Newton and then you will get this term which by minus 3 G Newton times mod W square.
In standard n equal to 1 supergravity, we do get this term, right?
Yes. So this is standard n equal to 1 supergravity. I am not saying there is anything different from standard n equal to 1 supergravity. Right? The reason that I am writing it down, because anything that you get from heterotic on Calabi, right, because it has n equal to 1 supersymmetry and because it has gravity, it must fit into this scheme. Right? So instead of writing down trying to look for the most general Lagrangian by considering all interactions, right, we know that it has to fit into this scheme. Right? So as long as you can determine these various functions, the k, the w, and the FAB, we have gotten everything. Then we can write down the action from there. Then it just saves some work that you don't have to determine every interaction individually. Right? You only have to determine these functions. Okay, for example, the fact that the Gij, the metric which appears here, is also the same Kähler potential that appears here. That's a consequence of supersymmetry. Right? The various terms here are related because of supersymmetry. Right? If you didn't have supersymmetry, you could write down the most general Lagrangian, right, where all these coefficients will have nothing to do with each other, and you could still determine them by comparing with what you get from the heterotic string S matrix. Right? It will just increase your one. Is that point clear?
No, I am still not clear. G Newton tends to 0 limit.
Yes.
When you actually do the say heterotic string scattering,
Yes.
and then try to figure out what the effective action should be.
Yes.
If I do not take the G Newton goes to 0 limit, I will see that term, right?
Yes, definitely.
You were saying something about you will not normally see this term
In the global supersymmetry.
Oh.
Right? If you try to take the global supersymmetry limit, then you don't see this term. Right? All these terms you can see from scattering, because this is the general action that must be there, right? This is the general structure that must be there if you have n equal to 1 supersymmetry, right? So if the scattering S matrix, right, computation gives a structure that is not this, then that means that the compactification breaks supersymmetry. Is this clear?
I was trying to see this term from superspace Lagrangian. There will still have b to theta w, right? The superpotential term.
Yes, but you have to use supergravity form, right? Superspace Lagrangian will also have to be accompanied by appropriate Kähler potential and so on. Right? So you have to do superspace, but in the supergravity context, right? Not the simple superspace, which is for global superspace. I think you can probably find this in Weiss and Dagger, right? Where they discuss n equal to 1 supergravity. This general structure. Okay. So let's as I said, get back to heterotic string theory on Calabi-Yau 3/4. What kind of fields do we expect there? Okay. So first of all, some things are common to what we had in type 2 theories, because the NS sector, okay, NS sector of type 2b are all there in heterotic. Right? If we just compare the bosonic fields, right, NS sector of type 2b is the same as the NS sector of heterotic, or the NS sector of heterotic. If you leave out the gauge fields, right? Heterotic theory of course has this E8 cross E8 and SO102 gauge fields which are not there in type 2. Okay? But at least this subsector without the gauge fields of heterotic coincides with the subsector of type 2, okay? At least at the level of supergravity. So we can read out the action, okay, for those fields in heterotic on Calabi-Yau 3/4 by knowing the action for those fields in type 2 on Calabi-Yau 3/4. Is this logic clear? Because it's the same action you start with in 10 dimension, right? It's the same Calabi-Yau you are reducing it on, right? So how can you get a different answer?
There is more supersymmetry.
They are more supersymmetry, but if you just look at the bosonic part, right? The dimension reduction doesn't care about supersymmetry. You could have done dimension reduction without caring about supersymmetry, right? Okay. So what I am saying is that if you look at just the NS sector of type 2 string theory and dimension reduce, you get what you get, right? It has to be consistent with supersymmetry, but that's an extra input. You could have not used that information at all, right? What supersymmetry you have. You could have just directly done dimension reduction. Okay? The result would agree with what you had gotten in type from supersymmetry considerations. Similarly, in heterotic theory, because it is the same supergravity, same bosonic action, okay, the NS sector of heterotic, when you dimension reduce, you could have dimension reduced it without ever talking about supersymmetry. Okay? And these two should agree. Is this point clear? Okay, that's the logic, because we use supersymmetry to fix the structure of the action, but we didn't have to do it, right? We could get the, in principle, you could get the full action by dimension reduction. Okay. So, the complex structure, so the action involving metric, 4D metric, complex structure, scalar moduli, and two forms are identical as in type 2 on Calabi-Yau. And for type 2 here you can use either 2A or 2B. Okay? Because these two theories differ in their Ramon sector, but in the NS sector they are identical. Okay? So you could either use 2A or 2B.
Here we are making no statement about super partners of this.
No, nothing, because we never wrote down the action, the supersymmetric part of the action anyway, right? And the point is that the super partners will be figured out automatically, right? Because given this data, right, n equal to 1 supersymmetry fixes what the full Lagrangian is, right? I have not written down the formulaic Lagrangian, but you don't have, that's already fixed by all these functions. Okay, so our goal is to determine all these functions, right? And right now we are determining it not on these functions, not for general field configuration, but in a restricted class where only these fields are going to keep. Okay, the fields that you get just from reduction of metric, 2 form and dilaton. Okay, I should also write dilaton, 2 form and dilaton, 2 form and dilaton. Now let's recall that when we have 2B, then the complex structure moduli of 2B are the vector multiplet scalars. Okay, they don't mix with anything else, right? Vector multiplet scalars are all coming from complex structure modulus. So that action, okay, of complex structure moduli will go over without any change to the heterotic theory. Is that logic clear? Right? The complex structure moduli, okay, are all coming from internal components of the metric, right? In type 2b. So when the dimension are reduced, okay, all those modes are there. Their action will be exactly what you had in type 2b. So this gives you that the K of complex structure is, what did we find there? Log of minus log that, which you can also write as minus log minus I by 2. This is the general formula, minus zeta I bar zeta I Fi bar minus. Okay, well, let's look at this form. This is more explicit. Well, more explicit in some way, more implicit in some way, because omega contains information of the complex structure, because you have to decompose it in, what linear combination of the fixed three forms it is depends on the complex structure. Okay? So this is the complex structure. So this, then, that means the scalar potential of the heterotic involving the complex structure moduli will contain this term. Is this point clear? Okay, because this structure is the same as what we had in type 2. Right? The scalar potential entered the scalar kinetic term in the same way as in heterotic and type 2b. Okay. So, because you know that the type 2b action and the heterotic action must be the same for these fields, we know the scalar potential for the complex structure moduli fields in heterotic must be given by the same result that we had in type 2.
So here Fi is not defined as del F del I. Del I. Fi is just defined as something.
Yeah, well, you could define it as del F del I, right?
But then you want an interpretation of F as anything in this theory. Because
well, not in this theory, the general n equal to 1 theory of course has no F, no P potential. Right? But this F is still the same function F that you computed on the Calabi-Yau. Right? So in this sector it looks like as if it has n equal to 2. Right? The scalar potential at least looks like as if it's inherited from n equal to 2, which is of course not a surprise, because this scalar potential is coming from type 2 on Calabi-Yau, which has n equal to 2. Yeah, but there is no, in general, no F. The general Gij bar that we have here does not follow from an F. Okay, individual pieces may follow from F, right? Like this one. Scalar potential is following from an F.
So would there be terms like complex structure multiplied by scalar moduli? So that scalar moduli, when you are switching off in heterotic, these are the only things that are remaining?
Well, if there are such terms in heterotic, they will also be there in type 2 because it's the same dimensional reduction, right? Both the complex structure and the scalar moduli are coming from the same metric degrees of freedom, right? So they will be very much there in, such terms will be present in type 2. But you know the type 2 doesn't have such terms. Right? So there cannot be any term of that kind. Right? Because in type 2, the scalar moduli are in type 2b, the scalar moduli are part of the hypermultiplet. Okay? Yes.
Can you please explain again why you took type 2b complex structure and why not type 2a scalar moduli?
Yeah, I'll take that.
Okay.
This is part of the, this is the K that involves the complex structure moduli. Right? Complex structure moduli is part of the chiral multiplex. Right? And the part of K which involves those fields will be given by this. Okay. Now the point is that we have to also now find the part of the scalar potential that involves the scalar moduli. Okay. This is only part of the Kähler potential, right? So the part of the Kähler potential that involves the Kähler moduli, if you are trying to determine it from type 2b, in type 2b they are part of the hypermultiplet, okay? And the hypermultiplets in type 2b of course contains the Kähler moduli, okay? The complexified Kähler moduli, both the things coming from B as well as coming from the metric, but it also involves Raman fields, right? So having this quaternionic metric is not very useful because you have to then understand what subspace of that describes the NSNS fields, okay? And in any case the quaternionic metric is not very easy to determine, right? You have to go through the C map and so on. So what we can do is that now we go back to type 2a theory. In type 2a theory we know that when we reduce on Calabi-Yau threefold, there the complex structure moduli becomes part of hypermultiplet. Their action is complicated, we don't know directly, but the Kähler moduli are part of the vector multiplets, right? And the vector multiplet scalars come fully from the Kähler moduli. So the action involved in the Kähler moduli can be easily figured out by knowing what the action is in type 2a supergravity or Calabi-Yau threefold. Is this point clear? Okay. So this tells us that 2a tells us that K of the Kähler moduli will be given by minus log or the volume of Calabi-Yau. This was minus log of volume, right? Yeah. Okay, and then hard derivative terms which will not worry about right now because we are not keeping all the other higher derivative terms. Is this clear? So you know that K for the heterotic should involve at least these two terms minus log minus I by 2 integral omega bar minus log of volume of Calabi-Yau. This is the volume of Calabi-Yau plus possibly other terms of course. But these terms,
So how does one fix the relative normalizations of these two terms? It just adds them. It follows from the supersymmetry.
well, because the point is that you didn't have any ambiguity in type 2, right? In the normalization of the Kähler potential. Because the normalization is given by this, right? The action is given by this. So the K was determined including the normalization in type 2. Right? Because if you change the normalization, you will get a different action. Okay, so it is really this. So these extra terms, they have the property that when you set the scalars coming from gauge fields to 0, these terms must vanish. Because when you have set the scalars coming from gauge fields to 0, okay, then the resulting field configuration is exactly what you get from reduction of just gravity part, right, of 10 dimensional action. N equal to 1 supergravity, pure N equal to 1 supergravity in 10 dimensional Calabi-Yau threefold, and for that we know that these two should give the complete Kähler potential. Any other term that we add here, which do not vanish when the other fields are set equal to 0, is in contradiction with what we know from type 2 and type 2. Is that point clear? Okay. So there are terms that we have to add, okay, but they will involve terms coming from gauge field reduction. Is this point clear? Okay, now what can you say about W for these fields? We again go back to 2A or 2B. We know that in type 2 or type 2b, the moduli fields have no potential, right? Otherwise there would be moduli.
They will get on from only gauge fields.
Yeah. So the moduli W, if there is a contribution to W, right? It must involve things, the scalars that are coming from gauge field reduction. Okay? If you set those scalars to 0, then W must vanish. Okay? So W is 0, okay, plus other terms. These dotted terms basically means that they must vanish when the scalar fields coming from gauge fields are set to 0. Is this point clear? Okay. Now, of course, this causes phenomenological problem, okay, which is the same as moduli fixing problem, that because W is identically 0, any value of the moduli is an allowed value. Okay. So, those are flat directions of potential, those are describing massless fields, okay, in heterotic string theory and Calabi-Yau 3-4, and we have to somehow find a mechanism to get rid of them. Okay. Now, this problem has been better understood in type 2 theories. Okay. So, I will discuss the moduli stabilization in the context of type 2. But in principle, there is no reason why one shouldn't be able to solve this even in heterotic theory using fluxes, okay, which I will discuss again in type 2 context.
So using the part coming from the gauge field reduction, it gets resolved. This is moduli.
No, it doesn't get resolved because the point is this, you can always set this to 0, right? And there are flat directions open up, right?
But you can also have compactification where you can fix everything.
I don't think there are any known
No, there's
compactifications where you can
there's
fix
no known
everything.
compactification.
Yeah, I don't think so. Actually, the dilettone will always be there. Okay. So now there is one more part here which was present in type 2, okay, and which you can use. That's the axion dilettone. Okay, they are also coming from NS sector, right? Type 2 theory has a dilettone, okay, and its super partner is the axion, which you get by dualizing the B mu field. Okay, so that field is typically called S A plus I to the minus 2 phi. So this phi, okay, let me emphasize here, this is the 4-dimensional dilettone. Okay. So this is really e to the minus 2 phi times square root of determinant G internal. Okay, so when you dimensionally reduce a string theory, right, you start with e to the minus 2 phi in front of the whole action. But then the square root of determinant G, okay, that's the volume of the Calabi-Yau also comes into play. Okay, so it's in fact it's this integral. Okay, so this part e to the minus 2 phi 4 that we see here is e to the minus 2 phi of the 10-dimensional dilettone. So let me call this phi 10 times the volume of the Calabi-Yau. Okay, because that's what appears in front of the 4-dimensional action. Okay, and this is important because this will change in a different context. Okay, so what you are calling dilettone, okay, or this field S, okay, will change from theory to theory. Okay, so that's why I am emphasizing this here. Okay. A is what you get by dualizing B. Now this field in type 2 theory is a hypermultiplier, both in type 2 and type 2b, right? The dilettone, okay, is in a hypermultiplier, and so that's the reason why the vector multiplier model action didn't get corrected. Vector multiplier moduli space didn't get corrected by string loop corrections, because string loop corrections is controlled by dilettone. Okay. So this trick that I described is not going to work, right? In both theories, it's in a hypermultiplier. Okay, so there is no theory in which it stands out by itself. Okay, it's part of this quaternion effect. Okay. But this, of course, is just one complex field. Okay, and one can work out explicitly what the corresponding scalar potential is. Okay, just by dimensional reduction. Okay, not by invoking anything in type 2, but just take the action, 4-dimensional action, and dimensionally reduce. Okay, see what kind of kinetic term you are getting. And from that you can figure out what its scalar potential is, and the result for this scalar potential of this is, I think, minus log. Yeah, so Ks is, so let me write it here, minus log of minus I times S minus S bar. Okay, so basically imaginary part of S, which is e to the minus 254. Okay, minus log of e to the minus 254. Is this clear?
Sorry, what is that term for?
This is the scalar potential. So this part gives the scalar potential for the complex structure, right? This is the scalar potential for the scalar moduli. Okay? But there is also the axion dilaton field, right? Which is not part of the gauge field, right? It was there even in type 2. Right? It's that there is no term in the type 2 axion which only had this, right? It was always part of the hypermultiplet. So I'm saying that this you can work out explicitly, right, by dimensional reduction of the axion dilaton moduli and see what kind of term you get, and comparing with this structure, you can figure out what the scalar potential is, and this is the scalar potential you get there.
I mean, the contributions from the gauge fields, from the scalars coming from the gauge fields will still be there.
Yes, plus, yeah. So minus this and plus dots. Okay, and again W will not depend on this. Well, it can depend on this, but only through the terms involving the gauge fields. Okay? Because when the set gauge fields are all set to 0, even the dilaton expectation value is completely arbitrary. Okay? So W cannot depend on those.
So this expression is correct to leading alpha prime and tree level string theory, what you have written.
Yes, exactly. So right now what I am doing is leading alpha prime and tree level string theory. Okay, so now we turn to the gauge fields. Okay. In fact, we will be focusing mainly on the scalar sector. Okay, but we will try to identify what is the unbroken gauge loop, which is straightforward. Okay. But our main goal will be to understand what kind of scalar fields we get, or what kind of final multiplet we get. Because by supersymmetry, once you understand the structure of the scalar fields, that also gives the structure of the fermions. Right? Because fermions, each chiral multiplet comes with a file fermion. Okay, so it will automatically determine what the fermionic spectrum is. Okay, so now let me just use some notation. So we will be using notation as mu running from 0 to 3. These are the 4D indices. 4D indices. M, this will describe the, this will be going from say 4 to 9. These are 6D coordinate indices. Okay, real coordinate indices, real. But this I can split into I and I bar because internal manifold has complex structure. Okay, so you can use complex coordinate. So these are the complex coordinate levels. Levels of CY3, and I'll also use another index, that is A and A bar. These are tangent space indices. Well, let me not call it A and A bar, let me call it R and R bar, tangent space indices. Indices of. Okay, we have not previously used the tangent space indices, but it will be useful to introduce this notation. Okay, And the compactification that we will be considering is the one where we identify the spin connection with gauge connection. But it's only in that case that you know explicitly what how to write down the low energy effective theory, because it's only when you set the spin connection equal to gauge connection, then you know that the sigma, as a sigma model, heterotic and type 2 become identical. Right? Both have this n equal to 2 to the power symmetry. Okay. So when you have set the spin connection equal to gauge connection, that means that what you have done is that you have picked an SU3 subgroup of E8 cross E8 and SO32 and switched on non-zero vacuum expectation value of this SU3 gauge fields, and those SU3 gauge fields are set equal to the corresponding spin connection, right? Because spin connection is also in SU3 because the holonomy is SU3. So you have taken these gauge fields, SU3 gauge fields, and point by point you have identified them equal to what the spin connection was at that point for the parabola. Okay. So this part of the gauge field is embedded. So switch on gauge fields in this. Gauge fields. Okay. So what we expect then is that the gauge group will be broken, okay, because the full gauge group E8 cross E8 or SO32 will not commute with these gauge fields that you have switched on. Right? You have switched on background gauge fields. Right? So once you have switched on background gauge fields, then the symmetry group is automatically broken. Is this clear? Right? Because it doesn't preserve the background anymore, right? Suppose you have chosen the background gauge fields, okay, non-zero vacuum expectation value. Now you apply a gauge transformation, it will change the vacuum expectation value. It will embed in a different SU3 group, right? So that means the gauge transformation no longer is symmetric. So which part of the symmetry will be unbroken? That's the part of E8 cross E8 or SO32 that commutes with SU3. Okay? So the surviving group will be E6 cross E8 or U1 as SO32. Okay, because this is the maximal group that commutes with SU3. Okay. So 1E8 is completely unbroken because you have to pick the SU3 from 1E8, okay, and that E8 is broken to E6. Okay. Here, the way you choose, sorry, this is not SO32, this is SO26. That you first pick an SO6 subgroup of SO32, that's standard embedding. Okay, take the first 6 elements and pick an SO6. And then inside that SO6, okay, that's a rotation in 6 dimensions. But you can pick an SO3 subgroup, okay, where you just combine those 6 coordinates into complex coordinates. And instead of applying a general SO6 transformation, you apply an SO3 on those complex coordinates. Okay, that's this SO3. Okay. So a U1 subgroup of that SO6 remains unbroken, and this SO2 and 6 is unbroken. Now it turns out that one loop effects breaks this U1 eventually, okay, in this theory, but that's another story. Okay, right now we will be focusing on just tree level.
So U1, how does the U1 survey? Can you repeat the argument?
Yeah, because SO6.
Oh, I think SU4 and then.
Yeah, SO6 is SU4, right? And out of SU4 you are picking an SU3.
Oh, that's
right?
U1
So that, yeah,
that's
that
U1.
U1 is. So that U1 survives. Okay, but it only survives at tree level.
What happened? It's get broken at?
At one loop. Basically, the file of you generate a file of stub and then the
String one loop.
string one loop. Yes.
It breaks to some discrete group or it breaks to one?
Well, that depends on the situation that we have. Right? But at least the continuous group is broken. Okay. So first of all, then we expect that there should be gauge fields in this gauge group, right? Okay, those are easy to identify. A mu.
So it's a number of scalars. You already said how many color multiples you have, right? You already mentioned it.
No.
We have not.
No. So scalars are the most interesting part.
That's right. Not mentioned.
Yeah, I'll be describing that. Okay, right now I'm just doing the easy part, right? Gauge fields. Right? So this A mu, right? A will be generators of either E6 times C8 or U1 times S42. Okay, you just take this to be X dependent, no dependence on Y. Okay. And you can easily check that these satisfy the usual Maxwell of the Young-Mills equation. That if you take the original 10-dimensional Young-Mills equation, okay, all the derivatives in the internal direction drops out because we are taking these to be only functions of X. Okay. So these describe 4-dimensional gauge fields. Okay, standard dimension reduction. Okay, where you take normally you would write this as in a complete basis, right? A mu an times Fn, okay, where Fn is a complete basis of functions in the internal manifold. Okay. You pick Fn equal to constant, right? That gives massless gauge fields in 4 dimensions, which are gauge fields belonging to these groups. Pardon? 26, exactly. Okay. So now let's ask what kind of other fields we have, other massless fields you have. Okay. And the interesting ones are the ones, okay, which are off diagonal elements. Okay. So this index A, okay, this is an adjoint index, right? So this is 248 of A8. Okay. So let's now focus on this theory. Okay, because this phenomenologically this is more interesting, but once you understand this, you can also repeat it for this. Okay, so let's focus on this theory. So A was to begin with 248 of 8. Okay, but not all 248 of 8 behave in the same way. Okay, because the surviving group is E6. So you have to ask that how does this break up into representation of E6 times SU3. Okay. SU3 is the group which is broken. Now it turns out the 248, so this is a standard group theory. Okay. It breaks into 78-1. This is the adjoint of E6. Adjoint of E6. Plus 1, 8. This is the adjoint of SU2 of SU3. Okay. And then plus 327 plus 3 bar 27 3 plus 27 bar 3 bar. Okay, these are of course all singlets on the RRU8. Okay, because the group is 8 cross 8, right? It's 248 of 8 that you are. So these we have already seen, right? These give rise to gauge groups, right? The mu component of this. Okay. It's easy to verify that none of these give gauge fields in 4 dimensions. Okay, because if you take the mu component of this, okay, it simply doesn't get described massless fields. Okay, so for these fields, okay, we look for AM and these indices are labeled by alpha and A is the full index, so what should I use here? Well, say K and AM alpha by A1. Okay, so the meaning should be clear. So M means that you are considering internal components. Okay, we are looking for scalars out of these fields. Alpha is one of these 26 values, 27 values. Okay, 27 is a representation of E6, and K is one of these 3 values. That's the representation of SU3. Okay, you can first of all verify that this number adds up to 248, right? Well, I hope it does. This is 81 plus 81, that's 162. 162 plus 8 is 170. 170 plus 78, that's 248, right? The full 248 representation breaks up into representation of this subgroup. Is this clear so far what we are doing?
We are breaking in E6 cross E8.
Representations here. So to begin with, we have this A index to 248 values, right? AMA, right? Now that's 248 values, you are splitting into 78-1. These are adjoint of E6. We are basically splitting into representation of E6 times E6, right? E6 times SU3. Right? Because it is a subgroup, so any representation will split into some representation of the subgroup, right? Okay, and that's a relevant subgroup here, because this SU3, we switch on background fields in SU3, E6 commutes with the background. Okay, E6 is symmetry of the background. Okay? So our goal is to look for massless scalars from here. Okay, we can repeat it for fermions. Okay, but as I have been
What was the comment you made for the fields coming from the first two? 71,
yeah, so this one can verify it doesn't give any scalar field. Okay, because 78, for example, is not sensitive to any. Okay, this is because this is transforming the E6 represent. This is a singlet of SU3. Okay, if you are looking for scalar fields here, you are looking for basically harmonic one forms. See the component of this in the internal space is a one form, right? Okay, and it doesn't couple to the background gauge field.
because it's singlet of.
Because it's a singlet of E6 of SU3. Okay, so if you are trying to look for massless scalars from here,
Oh, you wanted to.
you will not get anything. Okay, because you are just looking for one forms, okay? And there are no harmonic one forms on a Faraday oscillator. Right? That you know. If it has a torus, then of course you will get something here because you could switch on constant Wilson lines. Okay, these ones are more complicated. Okay, sometimes you may get massless scalars from here. Okay, because this is also a one form, but this also couples to the background gauge fields. Right? So the problem is more complicated. Right? You are trying to solve a different equation than just looking for one forms. It's one form but coupled to background gauge fields. Okay.
So not just harmonic concept, appropriate Laplacian with the.
Exactly. You have to look at the appropriate Laplacian, and this sometimes you may get scalar fields which are basically boundary moduli. Right? This basically means that these are the scalar fields which allow you to deform the spin connection equal to gauge connection condition to something different from it. Right? Continuous deformations of the spin connection equal to gauge connection. Because see, once you switch on these, right, the vacuum expression is one of these. That corresponds to switching on internal gauge fields, right? These are the SU3 adjoint gauge fields. Okay? So switching these on means that we are no longer identifying the spin connection equal to gauge connection. Okay? So these can be there, okay? But right now we will not worry about this, okay? Because these are singlets of SU. These are singlets of E6. Okay? These will be massless scalars, uncharged scalars. Okay? They have to be dumped into the moduli fields, okay? Possibly with potential, in which case they will not have moduli. But so we will not worry about this right now.
But this is the most complicated one, that part.
This is the most complicated one. Okay, so this is what I think is classified by H1 of endomorphism of T. Okay, I'll describe this maybe a little later.
You know what?
I'll come to that. Okay, what T is, I'll describe shortly.
Sir, I'm confused. Do
Yes.
they have potential or not? Is it 1/8 or?
It may or may not have potential. I have not said anything so far about these.
Okay.
Right? If they don't have potential, they are moduli. If they have potential, then they are of course fixed. Right? They are massless fields, but they don't have. You cannot switch them on.
So
Right?
we will see that later.
Yeah, we'll see that later, but the point is these are not the most interesting ones. Okay, the most interesting ones are coming from this. Okay, for reasons I'll be discussing, because these, even if they are there, right, they are massless scalars. Right? So what can they do? They will give at most give massless scalars which are singlets of the gauge group. Okay, or they will give massless moduli. Okay, which will be basically be added to the list of moduli you already have. Right, and you have to fix them somehow by generating potential at loop levels and so on. Okay. So let's not worry about them right now. Let's look at these. Okay, how to get massless fields from these. Okay. So for this, let's expand it out. And the way we are going to expand is the following: am alpha k xy as phi n alpha. So let me see what this is. A complete basis of functions on functions in quotes. Okay, we'll choose appropriate if they have to solve appropriate equations. Sum over n runs from 1 to infinity or 0 to infinity with an infinite number of basis states. Right? N is basically the level in the basis state. Now notice that I have treated the index alpha and index k differently. Okay, these functions, okay, the what function we will choose here, okay, sum over n of course is running, okay, but what function we will choose here, okay, I am letting it depend possibly on k and m, the basis of functions. Okay, this one, but I am not letting these functions depend on alpha.
Alpha was which index?
Alpha was the E6 index.
That's why you are letting the internal one depend on only SU3 and not D6.
Exactly. Okay. Now why have I done that? Okay. The reason that I have done that is because since this is the E6 index, okay, for different values of this index, the equation that you have to satisfy is the same. Okay. Because what does so ultimately you are trying to solve the Maxwell's equation, right, in the internal space. You look for massless states, for example, you will have trying to solve Maxwell's equation in the internal space. Okay. So those will be sensitive to the background gauge fields. Right? Background gauge fields are SU3 gauge fields. Okay. So depending on whether you have taken k to be 1 or 2 or 3, okay, the element equation that you have to demand on this will change. Okay. But the relevant equation will not depend on alpha. Right? Because alpha is an E6 index. Right? So suppose you keep k fixed and change alpha, okay, it's the same equation that you have to satisfy. Okay? Because this couples to background SU3 gauge fields, but E6 there is no background gauge field, right? Is this point clear? So in other words, let me repeat again what I am saying. Okay? So first of all, I have expanded it. I can always choose to expand it like this. Okay? Now we want to look for massless scalars, right? So massless scalars means, okay, it's the same massless scalars. Will mean that constant phi n alpha x, okay, or x independent phi etc. will solve linearized equations of motion. equation of motion. This is a 10 dimensional equation, right? The original equations of motion are always inherited from 10 dimensions. So he said this is equal to constant substitute in the equation. Okay? So that equation will be some equation on this. And the point is that that equation that you will get for different values of alpha, it will be the same equation. Okay? Why it will be the same equation? Because what will the equation depend on, right? It will depend on covariant derivatives, right? Because you have it's sensitive to the background metric. Okay? So that of course will know about the various indices that this thing carries, and it will depend on the background gauge field, right? Because background gauge field will also affect the equation of motion. Okay? Background gauge field is SU3. Right? So if you have defined SU3 quantum numbers, the equations will change. Is this clear? But different E6 quantum number, keeping the same SU3 quantum number, will not change the equation. Okay, so this will factor out, and you can write the equation simply as an equation for this. Okay, even though to begin with we had the product, we will set it equal to constant, and the point is that the equations that the linearized equations will not couple to alpha. This will just factor out. Okay. If, for example, you have factored this, put this here, okay, then what will happen? The linearized equations will not mix various things, right? Because the background SU3 gauge field acting on one K will give another thing. So you cannot write the equation separately for each f. Okay, they will be all mixed up. Okay, this is what you can avoid if you put the index k here. Okay, then they will be mixed up anyway, right? Because we are thinking of this as satisfying some equation, but this can be factored out completely.
And what was the reason that m was put with 8, not with 5?
Because m is the vector index of the internal space, right? And because there are covariant derivatives etc. acting on this, right? The equation will certainly mix different values of m. Right? When you typically apply covariant derivatives, it mixes different m's, right? So the equation that we will get will mix m and k. Okay? And the hope is that n, the functions will be choosing in such a way that for fixed n, that a different n's will not mix. Right? That's the way that last time we did it by choosing this to be eigen values of eigen functions of Laplacian. Right? So the different n's didn't mix. Okay? So similarly, n will try to choose in such a way that massless states correspond to some fixed values of n. It is also mixing between different n's. So linearized equation of motion then equation of motion will give you condition on f and k m. But now we do something, we split this m into I and I bar. I can always do that. This is the internal vector index, right? Coordinate index, I can split into complex coordinates. So f I bar into f I bar I into, and in fact what one can show is that these ones describe chiral multiplex, these describe anti-chiral multiplex, or vice versa. I mean, that's a convention. Okay? Because these will be the set of these fi bars and fi will be complex conjugates of each other. Okay? So one set describes chiral multiplet, the other set describes anti-chiral multiplet. Okay? It's very easiest to see from the formulaic viewpoint. Okay? Because for fermions, there is a clear distinction between what is chiral, what is anti-chiral, right? Because the chiral fermions are left-handed, anti-chiral fermions are right-handed. For bosons, of course, there is no right or left-handed, right? We are calling it chiral and anti-chiral just because of supersymmetry. Okay? But right now, let's assume it and go ahead. Later on, maybe I'll try to describe it in the context of fermions. Okay, now the index k. Okay. This index k is an SU3 index, right? It's a 3 index. It's 3 of SU3.
So here, f I bar is really taking fi and taking the conjugate of that is f I bar. Right?
Yes,
Because
appropriate n and k, right? You have to also change k to k bar.
K to right. So 3 to 3.
Yeah.
So they are one forms.
Pardon?
So these are one forms.
These are one forms, yes.
So like just by the same reasoning, v1 is 0. So
But these are one forms, but they also carry a vector index, right? So these are not satisfy the standard one form Laplacian equation. They are the derivative that is acting on them, okay, is sensitive to the background gauge field.
So same reason as is 180.
Yeah, the same reason that is 180, right? But otherwise you could have just set it equal to constant. Or not constant. You could have set this equal to 0, right? Because if these didn't carry any internal gauge index, these are also one forms. And there are no one forms in the internal space. Okay, but the situation here is more complicated because of coupling to gauge fields. Okay, now this index k is an SU3 index, it's a gauge index. Okay. But because we have set the background gauge field equal to the spin correction, okay, instead of thinking of this as coupling to the background gauge field, we can pretend as if it's coupling to the background spin correction. Is that clear? Because the gauge fields are set equal to spin correction, right? So the equation that we will be getting, okay, will be identical if this index had not been the gauge index but the index carried by spin correction. Right? So we can replace this k by what the index did I use for tangent space? A, right? R.
so this is only possible in standard embedding.
In standard embedding, yes, that's right. Okay, where we set the spin correction equal to gauge correction. Is this clear? Okay, so this you can think of as 0-1 forms valued in the holomorphic tangent space. For this one, it will be 0-1 form valued in the anti-holomorphic tangent space because this is 3 bar, right? So 3 bar will be similarly replacing by R bar. Okay, otherwise the logic is the same. So these are what are called H1 of T and H1 of T bar. Okay, H1 because it's one form, okay, but this bracket, whatever is in the bracket, okay, tells us that it's not a one form, it's actually one form valued. It's not a one form which are valued in number space, right, but it's one form valued in the tangent space, okay, because this carries this index R. Is this point clear? Okay. So linearized equations of 10-dimensional theory.
So for example, this one will be H01 of T, that will be H01 of.
Yeah. So the point is this: you always call it H1 because when you do Delbar homology, you don't write H01. Is always, yeah. You think of this only the one form, right? It's a H1, and you call this T validation.
And the other one will be.
This one will be H. Well, you don't. This is you just think of as complex conjugate of this, right? Its complex conjugate is F I bar R bar, right? So you, yeah. So you think of the H1 of T bar.
It's coming from the other one.
Exactly. It's coming from the other one.
Okay, or otherwise one could have thought as H10 or H01. I mean,
Yeah.
we don't write it that. We just think of
Exactly.
and
So you always
coming
use
from
only
the
Delbar homology, right?
Always Delbar.
Yeah. And any other index, right? If it's PQ, right? That Q you raise and think of as a tangent space index. Yes.
So if we think of this as SU gauge index, SU3 gauge index,
Yes.
when I go from one patch to another patch, the transition functions, they will not know about this gauge index. Those will be overall multiplication kind of stuff. But if these are tangent indices,
Yes.
then this when I do this transition functions, then tangent stuff are sensitive to that. So,
Yeah, but the point is the identification that you are making, right? The gauge fields are set equal to spin correction,
yes.
right?
But connections tell us how we parallel transport stuff. They don't tell anything about transition functions. I mean,
The omega AB, right? Tells us the omega AB are defined in each patch, right?
Yes.
But when you go from one patch to another, okay, you have to say how the omega is here and transform to omega is there, right?
Right.
There is in general local Lorentz transformation that you have to make to relate the omegas here to the omegas there, right?
Right.
And the point is you have to also make gauge transformations typically to relate the gauge fields here to that gauge fields there. And when you are embedding the spin connection in the gauge connection, right, that means the same transition functions will relate the spin connections as well as the gauge connections. Is this clear? Okay, so there is some equation, linear equation on these that you have to solve. Right? We have not written down what the linear equation is, but the linear equation is inherited from 10 dimension. Right? The 10 dimension Young-Mills equation in the background. Okay? That is what we are trying to solve. Now it turns out that when you have a Ricci flat manifold, scalar Ricci flat manifold, those linear equations that you get have a very simple interpretation. Okay, and that's what I am going to describe now.
Would be any issue with such a form existing globally in global systems of such form?
So when you say that you are looking for a solution, right, you are looking for a solution that exists globally. Right? Because it has to follow the transition functions, right? You solve it in each patch and then you have to make sure that between different patches it solves the transition function, right? When you say that there is a holomorphic one form, that's what you mean, right? That it has to also match up between different regions. So when you are looking for solutions, you are looking for that, right? A solution where in different patches it matches the backward transition function. Okay, so if I bar r, okay, let's forget about the index n, okay, that will just float around different, how many different n's there are, okay, we will determine. If I bar r, the first thing is that we can convert this to the coordinate index using the Fiat lines, okay. So we convert this into E A J to the Fiat line. Sorry, why? Because it's 6 dimensional Fiat line, okay? Then we can
So what is it?
R. Then we can lower this index using the holomorphic free form that we have, omega j j prime j double prime. Okay. So this is an object whose index is f I bar j prime j double prime, right? Looks like a 2-1 form. It's antisymmetric in j prime and j double prime. So what is non-trivial is a linearized equation that you get from on this from the 10-dimensional supergravity is identical to the condition that this object is a harmonic form. Okay, and you know how to count these, right? How many such harmonic forms are there? That's H21, right? So there are H21 solutions. To this equation.
But background gate field turned on, that changes the equation. So
Exactly. So because of that, right? If you didn't change the Laplace equation, then you would have been solving for one form, right? 1-0 forms,
yeah.
right? Because the background gauge field turned on, right? So what is said is that you can replace the effect of the background gauge field, okay, by thinking of this as a vector index, okay, or tangent space index, okay. So it's only after that that the equation was a harmonic condition on this. Right? Otherwise, you would have solved for 1-0 forms, which you know there are no harmonic 1-0 forms, right? If there is no background gauge field.
Yeah, the same represent your spin connection equal to gauge connection.
Exactly. Okay. So once you have replaced with a vector index, right, then you can forget about the background gauge connection, right? Because then you are thinking of this as ordinary tensor, okay, with no gauge index. Okay. The fact that the gauge index can replace a vector index you have used in the because you have embedded spin connection to gauge connection. Okay. So this tells us that the number of 27s, number of chiral multiplet in 27 is H21. Because why 27? Because you see that this 3 is correlated with this 27. Then we assume that this is in the 3 representation of SO3. Right? That automatically gives 27 representation of E6. Now we can do something similar for the other one. For 3 bar, we will have a similar thing except that we will call it G I bar N R bar. Yeah, this index will now not be the tangent space index, it's a holomorphic index, but it will be anti-holomorphic index, right? Because it's transforming in the 3 bar of SU3. Okay, just repeat the same analysis, but this will be 3 bar. Okay. So what we can do now is that we again multiply by E R bar J bar, and then multiply it by G. This is the, maybe I should call it G, I should call it H. This object is the metric H. G J bar L. Okay, so this has the structure of H I bar N. Okay, this is a metric.
And H I bar in R bar is same as Fi in R star, right?
Yeah, it will be the same as Fi in R star. So you are not counting those separately, right? You are only counting these with I bar index, right?
So that's why in this 27 counted did not include this, because that will come from the 27
Exactly,
bar.
that's right. That will come from 27 bar. It will be like the complex conjugate of the 27 bar. Okay. So this object, again one can show that starting from the linearized equation for this, okay, which involves the Maxwell's equation in higher dimension, in 10 dimensions. Okay. We can translate it to what equation this H satisfies. Okay. And that's again the harmonic equation for a 1-1 form. And this clearly is a 1-1 form, right? Okay, and it's again a non-trivial thing to check that on Ricci flat Calabi-Yau manifolds, the linearized equations for this translates to harmonicity condition on this 1-1 form.
So what if you were to do something wrong and take, instead of G, take omega, say J bar, K bar, L bar?
Then the point is it will not be antisymmetric in I bar, J bar, K bar, right? It cannot be interpreted as a form.
Oh, it won't be antisymmetric in the first.
Yeah, first and the last two.
So then it won't be, so it's not an element of H3.
Exactly. So how you manipulate it, right? Basically is determined by the antisymmetric condition. You have to make sure that the final thing is has the right antisymmetry. Is this statement clear?
This counts the number of chiral multiplets in 3 bar.
Well, in other words, 27 bar, right? You don't see the 3 bar from the low energy viewpoint, right? From low energy viewpoint, we know that there is an E6 gauge loop, right? So this is the number of chiral multiplets. Number of chiral multiplets in 27 bar is H11.
So, what about the FIR?
Yes, so the FIR will be the complex conjugates of F I bar R bar. Okay? That's why you are not counting them, right? Because you are only counting chiral multiplets. And as I said, the complex conjugate of these are always anti-chiral multiplets, right? So if you count everything, then you will count both chiral fields and anti-chiral fields. Right? That's like counting the field and its complex conjugate. Right?
But if I use the first equation, I mean, like what you wrote above, so I would get a 3-0 form.
No, not a 3-0 form. Because the point is, if you put R bar here, right? There is no antisymmetry between these and those last two indices. That's why you not get a 3-0 form, right? That's the, I think, similar to what Anirban asked, that you can try to make all indices anti-holomorphic, right? What you're saying, if this was R bar, you could have done bar here and J bar, J prime bar, J prime, double prime bar. But the resulting object has 3 anti-holomorphic indices, but it's not antisymmetric in the last two and the first one, right? It's not a form. Okay, that's why the way to reduce it is the way I have done it in these two cases.
So you get here H11 because you can have G or B here, right? Either.
You can, well, see the point, these are not G or B, right? These counting is giving, it's not coming from G or B, our G or B also gave H11, right? A complex
So
field.
I was asking because otherwise the number of parameters will have, each chiral multiplier has 2 real degrees of freedom. So this will have given you H11 real scalars, not complex. So, but you need to have 2 H11 real scalars. So that's why you perhaps say G or B G bar.
Well, the point is there is also the complex conjugate you are not counting here, right? See, the point is the I bar J bar, right?
The Fi.
Yeah, if you had started from Fi, exactly.
So if I start with Fi bar, I just get that one straight on H21 complex H.
No, it's not complex again, right? H21 is still just a single number.
No, but it's doing. I mean H21 complex scalars.
That's because you add H21 plus H12, right?
Or equivalent is because it's F. I mean this can be complex. So I can I bar J prime J bar.
Yes.
But
So this can also be complex in general. Right? This is not metric. Right? So the metric degrees of freedom would be real. Right? But because this is not coming from a metric, right? This is a complex field in general. Right? So at this stage, H11 actually counts the number of complex degrees of freedom, right? Which is right. See, the reason that H11 was counting real degrees of freedom and H12 was counting complex degrees of freedom had to do with the fact that H11 the metric had a hermiticity condition, right? If you had worked with Gij bar plus Bij bar from the beginning, then it had no hermiticity condition and you could count it from the beginning as a complex field. Here there is no hermiticity condition on these to begin with, right? Where a complex conjugate of this is I bar, which you are not counting. Okay. That's the reason both count actually the complex fields.
And I could not have contracted the B field here rather than G.
I think
Because that is
the point is G.
Suppose
Okay.
I put B here. I mean,
B is the same as let's see. Yes.
because that's what I was doing. Is this H11 related? But I was thinking you can also put B. That will give 2 H11 real, equivalently H11 complex.
Yeah, I don't think that B is an independent object because you can always work in a vacuum where B is 0, right?
No, but
See the background equation that you are solving,
no, but you did turn on B, right? The B plus Ij.
that was run as part of the moduli, right? But you can always work at the point in the moduli space where that is 0.
But then this H11 H21 symmetry between 2A to B will be generic because you wanted B plus Ij to be there, right?
Yeah.
So here, why should B J bar L be 0? Because that is the natural complexified color class, which I thought will.
Yeah. But what I'm saying, even if that is 0, right? The B, the equation that this thing is satisfying is not sensitive to B.
Right. But
It's
only
a-
number become double if you could have also contracted with B.
But if you put B, which is different from G,
Yes.
right? It may not have solved the equation, right?
But B still must have certain solve the same Laplace equation. Won't it? I mean,
No, it may not solve
because
the
B plus Ij is the complexified Taylor class, so both should simultaneously, I mean G and B should both satisfy.
See, G and B are basically counting the
That's
same
why they were parts of each
tensors,
one.
right?
Yeah.
They are counting the same tensors, but they are just complex. You are multiplied by a factor of I, right?
No, but that's why
Given
the
a
number
G-
was twice H1 rather than H1.
No, I agree. For the G, it is true. So what I'm saying is that if you had multiplied by B, right? Okay, That is equivalent to saying that you allow this to be multiplied by a complex number. So when you are counting the number of degrees of freedom.
I see.
Right?
Count.
Yeah. So I don't think it is going to give you
But what do we independent? I mean, what do we independent solutions? Because G have
not if you allow these to be complex to begin with. See, if you take allow these to be arbitrary complex numbers, right, then they will not be independent, right? Because what they are going to allow you to do, okay, is that instead of taking a given candidate for G, right, you are multiplying it with an arbitrary phase.
Or even if they are not proportional, you just absorb it in the normalization of H.
Exactly, yeah.
So it's not a different, it's not counting different.
Yeah.
Even apart from that, I mean, if I use G by B, the condition I get on H defined that way will be different from the condition I get on H defined this way.
No, it will still be H11, right?
Yeah, H11 from the digital equation that you get on that object.
No, the same equation, right? Laplace equation.
No, but it's G, and that derivative on G can have some consequences.
Yeah, but G is covariantly conserved, right?
So is,
and what is so is B.
Because
B is also a
zero.
candidate.
Same equation.
Yeah.
What is the number count doesn't matter.
Yeah, I think number count will not matter, right? It may just give a different linear combination of the same objects.
But it's twice H1 real because of this conjugation trick which gives you the
Exactly. Yeah. Okay, so the conclusion then from here is that from these fields, right, you get 27 representations of A6, okay, which are in the chiral multiplet, and the number of 27 representations is H21, number of 27 bars is H11. Okay, so maybe I'll stop here. So tomorrow I'll do the fermions, okay, just to demonstrate why this I index, this I bar and I index determines the chirality. Okay, because as I said in terms of scalars, right, scalars don't carry any chirality by itself, right? We call them chiral or antichiral just because they are part of a supermultiplet which contains chiral and antichiral fermions. So it's easiest to see this explicitly in terms of fermions, if we do a dimensional reduction of the fermions. Okay, so that we'll do that tomorrow first, and then we'll go ahead and see what kind of superpotential it has, what kind of Taylor potential it will have, and so on. Okay. And I'll also discuss the phenomenology, because for phenomenological purpose, these 27 and 27 bars are contains in fact the quarks, leptons, higgs and everything. Right? When you think of this as a grand unified gauge group, you can see that the quarks, leptons, higgs, all of these fit inside 27.
So this one will also give H21 scalars, this one which you left out, the 1 8. This will adjoin to this.
Well, this one H1 of endomorphism of T, right? Because this is carrying 8 index, right?
Oh, so not 3.
Not T. Right? So that's why it's called endomorphism of T.
Oh, it's
Because-
endomorphism, not T. Not
because the adjoint action is like is a linear transformation on T, right? That's how you can think of an adjoint. Okay, so this is another topological number. So number of scalars that we get from here will be H1 endomorphism.